This is K2. It's one of the tallest mountains on planet Earth. It's extremely steep at places like this and borderline flat at camps like this. Wouldn't it be nice if there was a way we could express this all mathematically? It turns out a bunch of really smart guys already figured it out 400 years ago. We can express the slope of literally anything if we know the function of what we are taking the slope of. From now onwards, I'll be referring to the slope as the derivative. Take a look at this function. We can see that the derivative of this function is constantly changing at all points. This indicates that the function is not uniformly steep everywhere. But wouldn't it be nice if we could know how this derivative changes as we move the function? It turns out we can just take this derivative as a function and then find its derivative to find out how it changes as we move the function. This is called a second order derivative. It tells us how the derivative of a function changes as we move the function. Similarly, if we want to find out how the second order derivative changes as we move the function, we can take its derivative in a similar fashion. Now let's venture deep into the world of Taylor series. Take a look at these two functions. Do they have anything in common? If you are particularly observant, you might have noticed that they share a common point at f of 0. Now what I am going to say next might seem completely ridiculous and dumbfounded at first. But bear with me, everything is gonna turn out very clean at the end. Let's try to find a polynomial that models this function. For now, let's ignore all the other terms except the first, second and the third term. We know that the first term is going to be f of 0 or cosine of 0, which is 1. Now the question that remains is what the second term would be. Well, we can take the derivative of both the functions and then we are just left with b on one side and negative sine of 0 on the other side. So b must be equal to 0. This completely eliminates the second term. This leaves us with the third term that we can differentiate twice to find out c. When we do that, we get c as negative 1 half. Now let's do it for the fourth term, the fifth term, the sixth term, and if we go on like that, we'll get a polynomial that fits perfectly into the cosine function. Before I move forwards, let's just appreciate the sheer beauty of a thing that we have just seen now. Even if you are not particularly crazed about mathematics, I am certain that you will agree that this is truly mind blowing.